Computer security is an important attribute for Internet of Things or IoT systems. IoT systems interact with the real world. They sense, they may actuate, they tell us what's going on. Internet of Things technology is used in many different applications: smart homes, medical, industrial. Let's consider a simple manufacturing example. Here's a simple organization for a small industrial system that does some work on various parts that flow through the system. Parts are in a storage area, and they can flow in a couple of different ways through the tools. Now that's just the tools in storage and conveyor themselves. Let's look at the computer system that controls this. Each machine has a programmable logic controller, or PLC. The PLCs are connected on a network to a Scada system, which stands for Supervisory Control and Data Acquisition. The network may include both wired and wireless elements, and it may actually use several different network protocols. It may use Wi-Fi, may use Bluetooth, may use various forms of Ethernet. So these are all computer systems, but they have different configurations and different uses. The Scada system is a desktop-style system. It, among other things, provides an interface to the operator of the overall system. It coordinates between devices. It's typically not providing high-rate real-time control. The programmable logic controllers are embedded systems, so they'll use different types of operating systems. They will be much more responsive to real-time requirements. Let's think about attacks and defenses for a moment. The attacker may have any of several different goals. They may want to obviously disrupt operation, make it clear to the system operator that the system is being attacked. The attacker may, in contrast, want to introduce subtle errors that will escape the manufacturing process and cause more problems down the line. The attacker may also be interested in information. And of course, there may be a combination of these attacker goals. How can attackers make their attacks? Well, they can directly attack the Scada system using methods that might work on other types of desktop or laptop or server systems. They may use their entry into the Scada to attack the programmable logic controllers. It's also possible that one PLC can be used to attack another PLC in the network. Maintaining strong security generally requires both design time and runtime defenses. At design time, we can use root of trust in order to create signed programs that help ensure that the software has not been attacked. At runtime, we can use monitoring. We can monitor the activity of the PLCs, the individual nodes. We can monitor the network traffic itself. We can also monitor not just the computer side of the system, but the physical side as well. Cryptography is a powerful tool for the design of secure computer systems. Let's review two of those tools: public key cryptography and hashing. When a public key system is used to encrypt a message, the private key is used in the encryption process. The recipient uses a different key known as the public key in order to decrypt and receive the message. This is an important building block, but we need to create higher level techniques. Hashing functions are another important tool in building secure systems. A hashing function might be used on readable text. In our case, we're interested in hash functions that can be used on program code. The hash runs through the message, whatever that may be, and creates a digest. This is a much smaller version of the original message, the programmer, etc. There's a very small chance that any change to the message would result in the digest being the same. If the digest we compute from the message we received is the same as the digest we receive from the sender, then we're confident that the message was not changed in between the time the sender created their digest and the time that we received the message itself. If the digest that we compute for ourselves from the message is different from the digest that we receive from the sender, then we know that the message was in fact tampered with. Now let's consider how to use public key cryptography and hashing to help us improve the security of our IoT systems. So for example, the Scada system might want to install some new PLC software on this node. Rather than just send the raw software, which could be intercepted at several different points and modified by an attacker, it will send signed code. The PLC can examine this signed code and ensure that it has not been tampered with. Let's see how to do that. The signed code has several components. It has, of course, the code itself. We can generate a hash function for that. The signature also includes an encrypted digest of the code. We decrypt it. We can then compare the digest that goes with the signature with the digest that we generate from the code itself. If they're the same, then we're confident that the code has not been modified. If they're different, then we have a problem. The signature also includes several other things. A signing certificate tells us something about who created the signature. But of course, the attacker may already be inside that PLC or whatever node we're installing on and may be ready to attack the code after it's been unpacked from the signing structure. So we need root of trust to help us maintain the security of each node. We start with signed code, and we then create an execution environment with what we call a trusted program. Trusted programs can start other trusted programs. Eventually, we can start untrusted programs. Untrusted programs have less overhead and are more appropriate for the actual system functions. But we need these trusted programs going back to a root of trust in order to ensure that our code is safe. To summarize, IoT systems are computer systems, usually networked, that interact with the physical world. Security is an important attribute for IoT systems. We can use both design time and runtime methods to monitor and enhance the security of our IoT systems. Code signing is an important technique for helping to ensure that the software that's installed in our IoT system has not been modified or compromised.